There we go. Okay, showing. Cool. Excellent. Thank you. Oh, where'd our speaker go? Here he is. Are you ready, speaker number one?
Ready as I'm going to be.
Well, hello, everybody. Welcome to our first Energy Bites. Woohoo! Our first one. So happy Friday. We have two exciting speakers today from the Cooling Center. Our first one here is Matt. He's going to give you an update on the cow cooling, I think. We're going to find out. So this gives you a pocket. All right.
All right, so I'm Matt Stevens. I'm a staff engineer at the Western Cooling Efficiency Center, for those who don't know. And I'm going to talk about a dairy cow cooling project funded by the CEC. All right, so this is a project funded by the CEC to develop a more efficient, more water and energy efficient cooling strategies for dairies in California. It's a 4-year project. It is led by the WCC with support from the UC Davis Animal Science Department and Integrated Comfort in West Sacramento. Okay, so for those of you who don't know, there are a lot of dairies in California. There's nearly 2 million cows, and most of them are located in climate zones 12 and 13. Climate zone 12 being our climate, and 13 being the Fresno, Bakersfield, Southern Central Valley area. So pretty warm. Dairy cows, there's a picture of Holstein on the left. That's the most standard breed. Produce over 8 gallons a day of milk on average. So some high producing ones produce a lot more, and lower producing ones produce less. But they have been bred for decades to produce more milk. You can see very large udders to hold a lot of milk. Milk production produces a lot of heat. It's an exothermic process. And so if the body temperature isn't maintained, their milk production can go down, the reproduction and fertility can go down, and disease susceptibility and mortality can go up. Fertility is important, especially because cows will not produce milk if they don't get pregnant and have a calf. So very important. You can see these cows here in the picture is their only method for getting rid of heat is panting, pretty much. It's not very efficient. So this is a typical cooling strategy for a dairy. This is the on-campus dairy. It uses water to spray, wet the cows on their back. That's a cow in the feed area, so they spray them in the feed area, and then there's a fan in the bed area that you can see over here on the right. So they get wet in the feed area and then go lie down, and hopefully the water will evaporate off them and cool them. So for our first demonstration, this is a bird's eye view of the campus dairy. We were in the yellow circle highlighted, or square. We tested 4 methods. The baseline, which I just mentioned previously, has a fan in the bed area and sprayers in the feed area. The optimized baseline, where we decided to try and co-locate the fan and sprayers to hopefully evaporate more water and cool the cows better. The conduction cooling mats, where water is circulated through these mats buried below their beds to hopefully cool them while they're laying down. And then these convection cooling the ducts system, where we have evaporative coolers with ducts and nozzles to direct cool air over them in the feed and bed area. So here is a layout of the actual layout of the dairy. We had 2 pens which were separated to prevent influences from either system affecting the results. The blue beds are the ones that we actually tested, And on the right, you have a picture of what the cross-section of the bed looks like. It's a concrete frame that's filled with sand, and the cows can dig it out to make it more comfortable for themselves or what. So this is the treatment schedule. Essentially what this is saying is that each group of cows went through every type of cooling system, and that they were done on various days so that we got statistically significant results without, having to worry about one group of cows being underproducing and affecting the results of a single system. So this slide shows just that the air temperature was pretty consistent for all of our testing. None of the treatments had significantly higher temperatures than any of the other ones, so that we can accurately compare them. Here's the equipment monitoring we did. We did power monitoring on the evaporative coolers, the SWEC and the fans, water temperatures at the sprayer, and the SWEC supply and return. We also measured the temperatures at each of the mats, each of the beds where the cold water came in and was flowing through them where the cows were laying. We also measured water pressure and air temperature and relative humidity at the evaporative coolers, inlet and supply, and ambient conditions with a weather station that measured black globe temperatures, among many other things. So this is a more detailed description of the baseline and optimized baseline. On this diagram on the bottom right, this is looking down at the feed stall. So the cows would be putting their heads in from the bottom, and their backs would be sprayed by those two sprayers. The baseline was a 20% duty cycle, so a minute and a half of spraying time, and then 6 minutes off with the fan in the bed area, as mentioned previously. And the optimized baseline was less spray time with the fan in the feed area, so to evaporate more water. So we were only spraying for 30 seconds and then off for 4.5 minutes. These are the conduction cooling mats. On the bottom left, you see them before they are covered with anything. They're sitting on top of a rubber mat. Then they're covered, all the gaps are filled in with sand, and then we put a protective mesh over the top so the cows don't tear them up. They're actually pretty good at breaking things. And then that was covered with more sand. The mats are actually adapted from solar water heaters. They were custom made for us. So this is the SWEC, the sub-wet bulb evaporative chiller, and it's essentially an evaporative cooler that uses the exhaust air with a plate heat exchanger to cool the incoming air, so you can reach a lower wet bulb temperature and approach the dew point, ideally. But what we actually used was the water was the product we were using. So the bottom there, you can see the number 1 where the chilled water was circulated from the SWEC into the mats and then back. Here is the SWEC itself and the blowing layout. So this unit was designed to provide cooling for 12 cows, but because we only had space for 4 beds, we had to simulate the other 8. And so those 2 silver tubes you see are water heaters so we measure the incoming, or the water coming out of the mats that is warm, and then we heat up the remaining water to that temperature to simulate an additional load. Here's a SWEC performance. Left chart, supply water temperature is generally about near or lower than the outdoor wet bulb. The middle chart, evaporative effectiveness, you can see it increases as the wet bulb depression does. And wet bulb depression, for those who don't know, is the difference between the dry bulb and the wet bulb. It's a measure of humidity in the air, or AWA. And then the COP, you can see, was pretty consistent between 6 and 8, regardless of the wet bulb depression. All right, so what we're seeing on the left here is the SWEC going from being off to on, and you can see that as it turns on, the water temperature in blue, or the average bed temperature, is slowly decreasing to a certain, till it gets to a steady state. And it pretty much stays there regardless of how much the air temperature increases. And on the right, we are looking at bed temperatures when the SWEC is on versus the SWEC off. So you can see that we're getting about 10 degrees of cooling, or you could see. So this is the evaporative cooler, one of the evaporative coolers we use. They're just off the shelf. We hung them out of reach of the cows. That's why we have to use nozzles. Cows will break and tear down anything and eat it to their detriment. So we had nozzles to project the air onto them and still get some convective cooling without danger of them eating it. So it's just a plain evaporative cooler. It takes hot, dry air through the evaporation of water, is cooled and humidified. So evaporative cooler performance. Evaporative cooler, you can see that as the wet bulb temperature increases on the left, that the supply air temperature increases along with it. That's because it's limited more or less by the wet bulb. Evaporative effectiveness is pretty steady throughout all wet bulb depressions, kind of inverse to the SWEC, and COP increases with wet bulb depression because as that wet bulb depression gets larger, you have more cooling that can be done, evaporatively speaking. This is a quick summary of our cooling strategy. If you look on the left, most equipment turned on at 72 degrees, with the exception of the conduction cooling mats. That's because of the time it takes it to get up to, or down to the cooling temperature of the water. We wanted all of the treatments to be providing cooling at the same time of the day. So we turned it on a little bit earlier so it could get down to temperature before it got hot outside. And then we had additional sprayers that turned on at 86 degrees to prevent the cows from entering any dangerous body temperature regions. Okay, so there is more cows panting. One on the left is panting, the other is drooling. Those are characteristics of high respiration rate and that they're starting to get stressed. And then we monitored the body temperature internally, which was logged every 3 minutes. When I say we, I mean the animal science department. The respiration rates were measured every 30 minutes from 10 a.m. to 7 p.m. throughout the entire study. So there was somebody, a student, out there with a stopwatch measuring those. We also videotaped the cows to see where they spent their time, see if they avoided anything, if they preferred one stall over another. Analysis is actually complete now. Somebody went through every minute of that video and classified where the cow was, what they were doing, and how long they were there for. Milk production was also monitored. The cows were milked on our campus dairy twice a day. And yeah. All right, so this is just showing that the cows were relatively cool. The scale is a little deceiving because it only, it's not even a full degree. But their body temperatures were all within a healthy range for all of the trials. And then the same thing on the right, except it's shown in respiration rate.
Matt, what is the temperature of the body?
I'm going to say above 102 Fahrenheit. I don't remember off the top of my head.
P-value?
Oh, there we go. P-value. It's not on the notes. One of the slides describes it. I think it's the next one.
Okay.
Less than 0.05.
I think it has like a tendency if it's less than 0.1.
Okay.
Oh yeah, there's the note down
Yeah.
there.
So this is body temperature over from all the tests over, or hourly. There we go. So the stars show where the baseline and SWEC are significantly different. You see most of the other three pretty much trended together They cool off when there's no sun outside. They get milked about 4 a.m. and they have a body rise, and then as the sun comes out, it gets warmer and warmer. Then they get milked again at 4, and that's where that other drop is. They're all getting very cooled in that time period, and then it increases again. All right, respiration rate for the cows. Oh, hourly. So you can see in the morning that the sweat had higher respiration rates, which show that they were, or even early in the morning, relatively early in the morning, before it gets hot out, that they are already starting to experience some possible heat stress. And then that, where they start to converge with the other ones, is where the additional sprayers turned on. So they were all essentially getting the same amount of cooling. This one is showing that the milk yield did not differ by treatment. All right, so this is forecasting the number of hours in each climate zone above particular temperatures. You can see climate zone 13 is in orange, is significantly more hours than climate zone 12, which means more cooling for the cows. Some assumptions we used that we'll talk about on the next slide are for pumping 45 psi required for the sprayers, a 100 meter well depth and a 300 meter well depth, and a 50% pumping efficiency. So those factor into these power and water uses. So you can see on the left we're looking at water use. Baseline used significantly more water than the other ones. Once again, blue is climate zone 12 and orange 13. But on the right, you can see that it used pretty much in the range of the same amount of power as optimized baseline, which was the lowest. Optimized baseline, because it was spraying half the amount of water, used less water. And the mats in ducts, because they were only evaporating water, used even less. But you can see on the right, if we go back, that the ducts actually used a lot more power. That's because the evaporative cooler design is not particularly efficient, and they had to operate at a higher static pressure than they were probably designed to in order to get the appropriate nozzle discharge and get the actual cool air to the cows. So this was our path forward after that demonstration. We essentially ruled out the mats due to heat stress. They wouldn't be effectively installed. We wanted to improve the energy efficiency of the evaporative coolers, and so we had integrated comfort built as the CalCool 2.0, which is intended to supply 10,000 CFM. We lab tested that evaporative cooler summer 2018, and then we worked on further optimizing sprayer controls, and we are delayed our summer field test until this summer. So this was the CalCool 2.0. You can see it with a large plastic duct on the right. It is designed to serve 40 cows, whereas the other cooler only served 4. It uses 3 sections of evaporative media instead of 1, and has a 36-inch axial fan. And it was designed to provide that 0.3 inches of static pressure from the beginning. So the new evaporative cooler used a lot more power because it's a lot larger fan, but the airflow delivery efficiency was just over double, which makes it a lot more of a competitive case. Evaporative effectiveness, you'll notice, was quite a bit lower. That's just kind of a hiccup with the pump sizing and the header design, which is easily solved. There's that note at the bottom where if we double the pumping power, we're still at double the efficiency. So another thing we've been working on are occupancy sensing sprayers. We tried to we did successfully build some cow sensing sprayers that used infrared and electronically controlled valve to open and close when a cow was there, and they worked. Problem was they got fouled very quickly in the dusty dairy environment, and so it stopped working. So we pretty much tossed that idea out. So then we came up with a mechanical occupancy sensing sprayer. It's low cost. It only sprays water when there's cows, the same as the electronic one, but it actually works. So this was the valve that I invented. This mechanical lever, the red, gets deflected by the cow, either directly by them, or on the right you see a typical headlock. The cows put their head in there to eat, and as they put their head down, those arms move. And so it deflects that lever, it lifts the piston, and water is allowed to go by the seal at the top. This is the very first iteration of it installed at the campus dairy. Because they have a different headlock design at this part of the dairy where we were allowed to test it, we had to modify it. And so you see that bar that protrudes, that is deflected by the cow. When she puts her head in to eat, it pushes it up against the bar and then opens the valve and sprays water. So this worked, but there were some concerns with that bar protruding, potentially providing a safety hazard for the cows. So we also wanted to investigate fan speed controls, so optimizing. A lot of the dairies have small fans, but they're moving 36-inch diameter, but they're moving to larger ones, 50 to 72-inch. A lot of them are also getting the VFD option as well to get variable speed. So we want to investigate how we can control the fans to be more energy efficient, so only blowing full speed air when we need it, and modulating it when we can, while still maintaining an effective enough evaporation to keep the cows cool. One of the ways another additional way, not just cooling the fan, but swapping out the fan motor, is using a switch reluctance motor technology, which operates much more efficiently at lower speeds. Results are from a test we did last fall, a while ago, and it shows this was installed in an RTU, and what it's showing is that the entire efficiency of the fan, the motor, and the drive belt when installed. And you can see that as there's a definite efficiency increase at the full speed, but as you drop, the efficiency increase gets bigger because the SRMs are better at running at off design speeds. Okay, I'm pretty close, I think. Yep. So we also had part of our team interview some dairy operators, and we did some audits at some dairies to get an idea of what's going on there, so we can provide a solution that's actually feasible and that they would follow. So some of their concerns were familiarity, how new of a technology it is, if they don't believe it's going to work or not. Cost, part of that cost is maintenance costs, and they prefer technologies that are easily maintained and you can tell if they're working or not. And they don't need some specialist to come from out of the area to come fix it if it goes down. Okay, so this is their view on the ducts. They were interested by them, especially by the potential for efficiency. The cons are that it has a much higher cost than any of the other options that we're continuing to look at. It could be damaged by the tractors that are constantly driving through the barn at different times of the day. Installation is quite complicated compared to anything else because it's a custom design for each type of barn and each barn. So sprayers and fans, most dairies already have these, so they're very familiar with them. The ability to detect the presence of the cows they feel would save them a lot of water. But one of them argued that it might not be aggressive enough compared to the other ones. So our path forward was we had to negotiate with the CEC because our original contract was about testing the evaporative coolers and the mats, and we found out through our testing that those weren't necessarily the best options. And so we finally have an agreement with them and a dairy and area where we can test all three to satisfy our contract and get some good information out of it as well that might actually be used in the industry. So we're going to install the ducts at a small scale, the optimized fan and sprayer control at a large scale, and the occupancy sensing sprayers at a small scale. We're working with ICI to build a Calcool 2.1 to fix the few little issues with that, and then continuing the development of the occupancy sensing sprayer, and then doing a commercial test. That test is occurring this summer. Now that's it. Questions? Yes, there's already a patent filed on the valve.
To be able to rescope the work on a research contract?
I did not bear the brunt of it, so yeah.
I think the display with the occupancy sensor actually, for example, has one of the called Matt Hall the head gate. The deer here as he asked for one, and he told me about what they were intrigued. Great, but I don't know exactly.
Any other questions? Any other questions?
Curious about the cost.
It was mostly based on the upfront cost. The evaporative coolers themselves are not cheap. I don't know off the top of my head, but if I had to guess, I think the ones we used in our on-campus trial were around $2,000. And so scaling that up to something, well, first of all, there's not really that many coolers that would fit that application, but that's a significant increase in cost compared to adding a VFD or even additional controls, of replacing the fan even.
Pass the
Yes.
pass the mic.
Thank you.
Can everyone hear me okay? Yeah? Good afternoon, guys. My name is Armando Casillas, part of the Energy Graduate Group. This is a presentation on my thesis project I've been working on for a year and a half, so my baby, and it's the first time I've presented results, so pretty excited. So let's keep going. So anyway, the project itself is called Low-Cost Internet of Things Sensors for HVAC Duct Building Leakage Screening. Okay, so it's not showing up on here. Give me a second. Change there. Duplicate from beginning. Try. Maybe. taking a while for.
Maybe because it's pulling off the drive.
Yeah, let me see. Just yeah, it's not.
It's not copying either.
I copied it back to the desktop.
Okay. It's still not doing it? Okay, why don't you just use your computer?
Okay.
Okay.
Sounds good. All right, we're back. So let's get it started. So slide on the importance of building energy efficiency. Buildings use about 40% of the energy in the United States, which accounts for about 40% of the country's carbon emissions. Building envelope and duct leakage is a significant source of this energy waste. When you look at measures for energy efficiency in buildings, a common one is just putting insulation on everything and making sure everything is thermally sound. But when you do the numbers, when you seal these leaks, these building envelope and duct leakage, these leakages, you get way more bang for your buck as far as the energy sort of energy reduction you're getting from that. So an overview on leakage in buildings. The first type of leakage you'll get in a building is building envelope leakage. What this signifies is any sort of air escaping from your conditioned spaces. So if you see here, air can escape from things like the crevices in the doors, crevices in the windows, transition sort of pieces between the walls and the ceiling, even things like receptacle switches and boxes, so like your plugs, air can get through there. There's a lot of areas where this air can exfiltrate or infiltrate. This creates off-design loads in zones, so you need to basically heat or cool your zone a lot more because of the fact that air is escaping or air is entering from the outside. Another type of leakage is duct leakage. So this is air escaping from the ducts themselves before or after the fan return or supply leakage. This wastes energy due to increased fan power because the fan needs to now maintain a certain pressure to compensate for that drop in pressure from the leak. This wastes energy due to losses to unconditioned spaces. A building like this has ducts in an unconditioned space called the ceiling plenum or the attic. That's a waste of energy there, or ducts can exist outside on the roof, and that air escaping to the outside is conditioned, and that in itself is a waste of energy. So the current method of testing, at least for envelope leakage, is called a blower door. So you see here we have a trained technician strapping a wall of fans, a blower door, to pressurize, looks like a cafeteria, commercial building. You can see here there's a lot of wiring that needs to sort of be in place. I'm sure that he's not the only one on site. There's usually 2 or 3 people sort of making sure that when you do pressurize a building, things like the tape that you have to put on the registers, like the supply and return ducts, don't fall off or whatever. There's a lot of sort of like watching you need to do, a lot of man hours that goes into this. On the right, you see sort of the concept of a blower door. You pressurize or depressurize your building to a certain pressure and measure the airflow through that fan. What that sort of creates is a profile of leakage. So on the y-axis here you have the CFM, the amount of air passing through your fan, and on the x-axis you have the pressure set point. For each pressure set point you're going to get a different leakage number, and which you can derive is an equation, a slope, which is this K here, that gives you basically the effective area of leakage, and N being the flow exponent. So what we're proposing is an alternative method. Instead of using this invasive sort of process, you can just use the existing RTU, the rooftop unit on your fan, on your roof, to pressurize the building at the normal pressure it usually pressurizes at, And knowing the amount of air that is being taken into the building from the outdoor air intake, you can measure the pressure using these really cheap absolute pressure transducers, which are about $2 a pop. They're really cheap, and you could do what a blower door test does. So the basic idea for envelope leakage, like I said, you take a one-time measurement of the air going into this intake here, and you do short-term pressure response measurements for when the fan comes on. On the duct leakage side, you're going to be not only measuring pressure, but also temperature and relative humidity. These three data points, you can calculate absolute humidity or humidity ratio, which is the amount of water per kilogram of air. So sort of a common measurement is kilogram of H2O per kilogram of air of water. What you can do is you can use that to measure the change in absolute humidity between zones when the fan comes on, and you can use that as a tracer gas to measure leakage. We're using conservation of mass for both air and water, those principles, to come up with these measurements. This is just a quick picture of how we developed our sort of measurement for intake, outdoor air intake. We strap the duct blaster to the outdoor air intake. This is similar to a blower door, except it's a ducted sort of fan. We pressurize it to what we knew was the operating pressure of the outdoor air intake, or this area here, and we came up with a figure for that. So now going into the sensors themselves, on the left here you have a magnified view of one of the pressure units, one of the sensor units we have. You can't really see it here, but on the black there you have the temperature and relative humidity sensor, and the one right below it is the absolute pressure transducer. On the right here you have a setup we had in the lab. This is small little box is supposed to represent a building. We sent pressure signals into the building. One of the pressure sensors is stuck inside the building to measure the pressure change there, and one is placed on the outside to measure the pressure, and we can measure pressure differences that way. We also have a tube differential pressure sensor that does essentially the same thing. It's a lot more accurate, but it requires tubing, and the whole kind of idea of the project is how can we get these really cheap sensors to reduce the need for tubing invasive processes like this. But this is also an IoT-enabled sensor device that we use in both our lab test and field test to do a side-by-side with the absolutes. That just shows this differential pressure sensor is right next to the absolute pressure sensor. So this is a result from one of the lab tests. So we send a pressure signal into the little box and measure the pressure response with each of the sensors. The orange plot is a Validine sensor, which is a NIST-calibrated, super expensive, heavy-duty sensor that we use as a sort of reference sensor. The gray plot you see is a tube differential pressure sensor. It's pretty close on the money to what the reference sensor is doing, also pretty stable. The blue line, a little more scattered, is the absolute pressure sensor difference that we calculate. It is a little scattered, a little noisy, but for the most part, it is in pretty good agreement with the reference pressure signal that we're getting. So we transition over to our field test. This is the annual fun trailer. It's in the center of campus. This sort of like is a call center for donations and things like that. Their operation hours are from like 5 to 10. So, which was great, so we could do some ground truth testing during the day. We didn't really disturb much of the occupants. This is a simplified diagram of what the building layout is. There is a ceiling, a drop ceiling, so like an attic area where the ducts are housed, and the arrows here show every which way leakage can occur. So you have ducts, there's supply leakage into the attic area, you have return leakage. It's the ceiling plenum air going into the ducts that way, and you have air leaking from the room to the outdoor or from the room into the attic itself. Reality is, though, this was a building with 3 identical rooftop units, so things can get pretty hairy. There's a lot of things we need to sort of take into account, a lot of things we need to keep track of. We're measuring temperature, relative humidity, pressures in most of these zones. We had a total of 15 sensors, and that's sort of limited with the company we were working with. That's all they really had resources for is to give us 15, so we had to be sort of creative in where we were putting these sensors. But we were able to put most of them in the ductwork, one in the room, one on the outside, to measure changes in pressure and relative and absolute humidity. So just a quick overview of the test protocol. We are pressurizing the building using a Wi-Fi enabled thermostat. So overnight, we have a sort of test programmed that we send to the thermostat. The thermostat turns on, the fan turns on. You can either just put the thermostat in fan only, or we can also do cool or heating, depending on what kind of test we do. Envelope leakage, we're pulsing the building at a known frequency using the RTU. This requires pressure measurements between the unconditioned space, so the outside and the inside, via absolute pressure or differential pressure with the tubes. The duct leakage test requires monitoring of the absolute humidity change between zones, which I'll go into more detail later on. So this just shows one of the absolute pressure sensors where we placed it. This is the intake area, the same intake that we put a duct blaster on to measure the intake. We were getting pressure signals of about negative 20 to 25 pascals. This is with the absolutes. So with higher pressure signals, you're able to pick this up with the absolutes. And it's pretty neat to see the blue line being when the fan comes on and when the fan comes off. And when the fan comes on, you are seeing a very steady, sort of a stable reading of pressure, differential pressure change when the fan comes on. This is pressure readings with the tube sensor. So unfortunately, we did have to make a little hole in the screen to run a tube in. Ideally, this is the thing that we don't want to do out in the field in later projects to avoid sort of the invasiveness that I talked about before. But what you're getting here are, once again, very clear signals inside of the building for when the fan kicks on. About 4 pascals difference between the room and the outside. The orange line shows the difference between the room and the attic area. So that pressure difference is a lot smaller, around 0.2 pascals. This here shows the same pressure signal measured by the absolutes. Very noisy, like the previous plot. The good thing is that there is a clear response between when the fan is on and when the fan is off. What we do is just take a median response for these signals and compare them to the tubes. Yes?
Why is it so big?
Oh, good question. Great question. So the reason why is because each absolute pressure sensor pair, there is an inherent bias, a measurement bias between those two sensors. So just because you are getting a difference in pressure, it is going to have a sort of like set bias between both sensors. So what we're looking at really is the change in pressure when the fan kicks on and when the fan kicks off. And I'll go into that in a little more detail right now. So we first started off with 20-minute cycles, and then we went into 5-minute cycles with the sort of with the logic that with that we had more chances to measure that pressure response, and also we're driving the building at a frequency that might be a little less than what a temperature change could be. What you have here on the gray plots are the tube sensors, and on the green plot are the absolutes. You are seeing a response from the absolutes. What you do see, though, is a sort of like low frequency drift that tends to happen when there's a change in temperature in the building or on the outside. So the cool thing that you could do is, because we know how frequent we're pulsing the building, so we have 5-minute cycle on, 5 minutes off. That's a 10-minute cycle. That's 600 seconds, so 1 over 600 is 0.0017 hertz. So what you can do is you can actually get this sort of this wave that you created with the pulsing of the fan and filter around that known frequency, especially on the lower side, to get rid of things like drift, things like measurement bias, like I mentioned. So what you end up getting is a comparable sort of plot where you can actually compare the response you're getting from the tube sensors and the absolutes. It's still kind of noisy, and I'll show you what we actually do on this next slide. So we take the change in pressure, so that response in pressure from when the fan kicks on and when the fan kicks off, and you get this sort of sinusoidal square wave. And for the most part, things are in agreement. You have some outliers. We take those out, and what you get is some pretty good agreement between the tube sensor, sort of invasive sensor, and the absolutes around 0.2 pascals of a difference. So that's pretty darn good for a really cheap $3 unit sensor. Yes.
Can you describe again how you?
What was that?
Can you describe again how you?
Yeah. So the square wave here, what we're doing is we take the average pressure we read when the fan kicks on, and then when the fan kicks off. So you can think of it kind of like when you have like a scale, and you get something that's 1 pound. You put the 1 pound object on the scale. It's gonna read 1 pound, and you take it off the scale. It's gonna change -1. So what you're doing is you're putting on the item, you're taking off the item. And what you get is a change in one pound, and then the change in -1 pounds. And what you're going to see is this sort of hopefully a stable change in, I guess, the response. So when you put something on a signal and when you take it off. So this is a similar thing here. When you kick the fan on, you're going to see a change in pressure. When you kick it off, you're going to see a negative response. And hopefully, if your sensor is stable, the gray plot here is the tube, which is pretty stable. So you're going to see a pretty stable wave. The green one is the absolute. It's a little wonky in some areas, but for the most part, it is pretty close to what the tube sensor is doing.
One more. Can you go back to the last slide?
Yes.
So you took the average.
Yeah.
The high.
Yeah, exactly. High and the low, and you measure that sort of change. Yeah. So one of the tests we had to do is, we pressure the building at this as-found condition, and we pop a tile off, and we measure the pressure there. And what you end up getting is the sort of the flow coefficient for the whole building envelope. What you see here, we see a K sum. So with that K sum, you plug that into the formula, and we assume an N value of 0.65, which is sort of the understood, assumed flow exponent for envelope leakage. And what you end up getting is a value of around 1200 CFM with that calculated K. We did a blower door test. That's a very invasive process that we don't want to do, but we had to do it to sort of compare things. And what you end up getting is a value of around 1200 CFM for a 25 Pascal signal. This basically shows a pretty good agreement between the absolute tubes and the ground truth test. Yes.
Now, did you have to have
No. So what we did is we had that one-time outdoor air measurement we did.
But you had to have that number in order to.
Yes, exactly. Yeah, you had to have that.
Do you really think that takes less time or is less invasive?
Very good question. Yeah, that is a question I've sort of struggled with. One thing we've looked at is maybe having like a sort of wireless CFM sensor at the intake to measure these sort of things. You can do that, or you can also do a flow hood measurement test when you go visit the site for the first time. Yeah, there is a question of what's more invasive than the other. Is this one less invasive? The question really relies on logistics, and when you do these measurements, when we talk about invasiveness, we're talking about, with the blower door test, you basically need everyone out of the building. Things like that. With the outdoor air intake measurement, you're not really disrupting. Exactly. There's a lot of things that, you can still do with that. So I'm going to try to speed things up. Conservation of mass, it's kind of a fancy sort of word, but let's talk about conservation of color, basically. This is sort of like a simplified version for people who aren't really going to get this firsthand. So you have blue and red make purple, right? We all know that. Blue and purple make violet. That's a very simple concept. So you can sort of use that same thing for we're talking about mixing of absolute humidities in different areas. So you have the level of humidity in the room, blue, and the level of humidity in the supply plenum. Those two mix in the ceiling plenum to create a different, a mixed level of absolute humidity. Same thing happens on the return plenum. You have air coming in from the room and air coming in via return leakage from the ceiling plenum to make that violet color, to make a mixture of both of those humidities. And these are the humidity levels that we're monitoring to calculate return and supply leakage. Just an overview of the equations that we're using for this. These are ratios of these leakage flows for the supply side, and on the return side, we're doing the ratio between the return leak and the amount of air coming in from the return grill, using absolute humidities and densities. So this is the return leakage test that we conducted. This is a 1 hour long test. I think that's what the next thing says. 1 hour long test, and with the fan only operating. What you're getting here on the lower side of the plot is the levels of absolute humidity in the ceiling plenum, which is the attic area. The top line, the gray line, is the levels of humidity in the room. The orange, yellow lines are the humidities in the return plenum. So as I said before, that level of absolute humidity is going to be a mixture of the lower plot and the higher plot. And as expected, that's what happens. So when you pressurize the building, which is around here, becomes pressurized, you do see a stark change in humidity in some of the areas. So that orange plot is the third unit ceiling plenum, and that one consistently showed a lot more leakage than the other ones, just using this method here. So on the supply side, we had to get a little creative. You need a large enough humidity signal and a large enough difference between zones to measure that sort of mixing that we talk about. One way we found we could do it is if you put the unit in cooling, what you're doing are two things. You're making the room cool, which drops down the level of humidity in the room. At the same time, the cooling coil is really cold, and so when you bring in air from the outside, that air contains humidity, it condenses on the coil. So you have water condensed on the coil, you have a room that's extra dry now. You kick on the heating, and what you do there is you get that condensed water on the coil and you evaporate it. And what you do is you get these spikes in humidity. So these orange and green lines here are when the heating kicks on. What you're seeing is this huge spike in absolute humidity, and what you're doing is you're also getting a little spike here in the room as well because of the fact that all of a sudden you're bringing in all this humidity. And you have this very, very small window, like 10 to 15 minutes, where you can measure, I guess, the mixing happening between those zones. It's very transient sort of process, so sort of took a standard like 10 minutes after that heating unit kicks on. What is that mixture there? And we got around like 0.6 for that SR number that we're getting. Okay, so just really quick, this is the sort of derivation of the calculations that we're using for return leakage and supply leakage. We apply those to more tests, and given that SR, RR, and a bunch of other things that we do measure, we are able to calculate return leakage for when the fan kicks on. And what we're getting are pretty comparable results to ground truth, which is the sort of duct lasher test that you would do for duct leakage. With the sensors, we're getting around 16% return leakage compared to the fan flow, and with ground truth, we got 17%. Pretty darn good. On the supply side, this is a little harder to do. Like I said, it's you do need that pressure signal, but you also get in this particular test, we got pretty good agreement there. So just in summary, you can use building envelope leakage. You can use these inexpensive sensors to measure building envelope leakage, especially the pressure differences between the inside and the outside of the building. You still need tube sensors to measure very small pressure differences in between zones. I think the absolute pressure sensors are too noisy to be able to measure anything below 1 Pascal, essentially. Duct leakage, we can use this sort of absolute humidity, sort of tracer gas method to measure supply leakage or return leakage. Supply leakage, like I said, the test needs a little more improvement. The signals right now aren't good enough or aren't sustained long enough to have a clear sort of number. Future work, we're currently looking at another building on campus that has an economizing unit. We strapped a 0 to 10 volt controller to it, and what we're trying to do is modulate that damper and measure the airflow for each position, and also measure the pressure given for each airflow, and essentially creating a multi-point sort of test that you would be getting with the blower door, just with a remote automated system. So yeah, thank you very much. Appreciate it. Yes, Robbie. Yep. Yeah, bandpass filter. So we did some filtering on the lower side, especially the lower side, because the lower side is representing drift from things like temperature change and things like that. And on the higher side, just to get rid of some of that noise, we filter some of the higher frequencies as well. But it was a kind of a neat thing. It wasn't really deliberate either. It was just kind of like Mark saw one of my plots and was like, hey, that's a wave. You can filter that.
Was there a way you picked frequencies?
Was that?
Was there a way you picked frequencies?
No, once again, it was just like 20 minutes was a little too short, and there was enough time for the sensors to drift in that. So I said, okay, let's try 5 minutes. 5 minutes is sort of short enough time for that to maybe not have so much of an issue. So once again, 5 minutes on, 5 minutes off, and Mark saw, just when I showed him the plot for the first time, he's like, oh, that's a wave. You can filter that and get rid of some of that stuff, and that's what we did. Yeah. Any more questions? Thank you, guys. Appreciate it. Eject this.